ME347, Example 19. Water at 60 degrees Fahrenheit is to be pumped from one large open tank to a second large open tank. The pipe has a diameter of 3 inches and a roughness of 0.005 feet. This is a high value and corresponds to a very rough pipe wall due to chemical deposits or fouling. The remaining dimensions and minor losses are shown on the schematic diagram on the next slide. For Part A, determine the system curve for this application. For Part B, select a pump diameter from the Peerless 4AE12 pump family operating at 1750 revolutions per minute, where the required volumetric flow rate is at least 400 gallons per minute. Then, give the operating conditions for the selected pump. For Part C, calculate the efficiency at the operating conditions from Part B. Compare this value to the efficiency given by the manufacturer. For Part D, calculate the net positive suction head available at the operating conditions from Part B. Use this value to check for the likelihood that the pump will experience cavitation. For this problem, we will first assume steady, constant property flow of a Newtonian fluid, which is water at 60 degrees Fahrenheit. Second, we will assume that the water level in the large tanks is constant, that the water is open to the atmosphere, and that the velocity of the water at the top of each tank is approximately 0. Third, we will assume fully rough turbulent pipe flow for our very high pipe roughness. Let's begin by looking at the schematic diagram for this problem, which shows water being pumped upwards from a lower tank to an upper tank. The water in the lower tank first enters the piping through a re-entrant entrance with a loss coefficient of 0.78. Then it goes through 10 feet of piping and 1 elbow before the pump suction inlet. After the pump discharge, it goes through 40 more feet of piping and 1 additional elbow before flowing into the upper tank through an abrupt exit with a loss coefficient of 1.0. This corresponds to a complete loss of the kinetic energy for the flow in the pipe. For both of the elbows, the minor loss is given in terms of an equivalent length of straight piping. The specified value is given as the length of 30 diameters of piping. Note that the change in elevation of the water before the pump is 5 feet, and the change in elevation after the pump is 20 feet, so the total elevation change is 25 feet. Also, the total pipe length is 50 feet. For Part A, determine the system curve. To begin, we apply the energy equation for steady flow to a control volume that starts at Section 1 at the top of the water in the lower tank and ends at Section 2 at the top of the water in the upper tank. Thus, it includes all the water flowing from the lower tank, through the piping, accounted for by the major head loss term, through the entrance, exit, and elbows, accounted for by the minor head loss term, and through the pump, accounted for by the system head. Thus, the system head is the amount of head that needs to be added by the pump to overcome the losses and move the fluid through the system. Next, we can reduce this equation by first assuming that at Section 1 and Section 2, the water is at atmospheric pressure. Second, we can assume for the large tanks that the velocity at these sections is also 0. Finally, we can substitute in for the total elevation gain using Z0 and define a coefficient for the system curve given by C subsystem in terms of the head losses and the volumetric flow rate Q. To solve for the major head loss due to the friction in the straight pipe, we will use the Moody friction factor defined as shown. Note that for our control volume, we need to use the total length of the pipe. Recall that the friction factor in general is a function of the Reynolds number and the roughness of the pipe. Because velocity or flow rate is one of the variables in our system curve, we cannot solve for the Reynolds number directly, but will need to iterate for a value. We can solve for the relative pipe roughness of 0.020. Next, we will take a look at the Moody diagram, which plots friction factor versus Reynolds number and relative roughness. For our relative pipe roughness of 0.02, as long as the Reynolds number is above 50,000, the flow is in the completely turbulent or fully rough zone, where the friction factor remains constant with Reynolds number. To verify if we will be in the completely turbulent zone, we will calculate the velocity and volumetric flow rate that corresponds to this Reynolds number range. As shown, as long as the velocity is above 2.4 feet per second, or the volumetric flow rate is above 53 gallons per minute, the flow will be completely turbulent. Because the operating point for the flow specified in Part B is above 400 gallons per minute, it is indeed reasonable to assume a constant value for the friction factor for the portion of the system curve needed to select our pump. Based on this, for our relative roughness of 0.02, we calculate a friction factor of 0.0486 using a correlation for completely turbulent flow. Note that if the friction factor did depend on Reynolds number, we would need to iterate for the system head at each flow rate. Thus, we would probably want to use an equation solver such as EASE for our analysis. To solve for the minor head loss due to the entrance, two elbows, and exit, we will use the definition shown. For the two elbows, the head loss is accounted for by adding 60 diameters of pipe length. For the entrance and exit, the total loss coefficient is 1.78. Next, our major and minor head losses are combined to solve for the system curve coefficient. Notice that for this case, where the friction factor is constant, the velocity cancels and we get a constant coefficient of 93 seconds squared per feet to the fifth power. Note that if the friction factor did depend on Reynolds number, this coefficient would also be a function of velocity. Finally, substituting in our total elevation change and system curve coefficient, we get a simple parabolic curve for the system curve as shown. Note that because we want to plot head versus flow rate in gallons per minute, we converted the coefficient to units that make this calculation more convenient. This also makes our result a dimensional equation, thus the flow rate must be in gallons per minute and the resulting head will be in feet. For Part B, to select a pump, we first calculate some values for the system curve to plot on top of our pump curves. For a flow rate of 100 gallons per minute, we get a system head of 30 feet. Repeating this calculation at a range of flow rates, we get the values given in the table. Note that all of these flow rates are well above 53 gallons per minute, which is needed for the constant friction factor used for our system curve equation. Now, we plot this system curve on top of the manufacturer's pump curves for the Peerless 4AE12 pump family operating at 1750 RPM, as shown. The operating point for each of the pumps will be where the pump curve and system curve intersect. Since we need a pump that can deliver at least 400 gallons per minute, we must select either the 11-inch or the 12.12-inch diameter pump. For this example, we will select the 11-inch pump. However, in practice, we might want to get the larger pump because of the plus or minus 20% uncertainty typical for these calculations. From the intersection point for the 11-inch pump, we get an operating flow rate of 430 gallons per minute at a head of 110 feet with an efficiency of 73%. Next, we look at the additional performance curves for the Peerless 4AE12 pump family. At our operating flow rate of 430 gallons per minute, we get that the net positive suction head required is 7 feet and the operating power is 16.3 horsepower. Finally, a summary of the operating conditions for our selected 11-inch diameter pump is given. Note that the operating head is shown being calculated using the system curve. Of course, this value should be the same as the one that can be read using the intersection for the pump curve. For Part C, we want to calculate the pump efficiency based on the operating conditions given above. First, we recall the definition for the pump efficiency that compares the hydraulic power delivered to the fluid to the mechanical power put into the pump shaft. Second, we recall the definition for calculating the hydraulic power from the pump head. Using our operating point conditions, we get a hydraulic power of 12 horsepower. Dividing this by the mechanical power, we get a pump efficiency of 73%, which is consistent with the value obtained earlier from the pump curves. For Part D, to calculate the net positive suction head available, we begin by applying the energy equation for steady flow to a control volume with an inlet at section 1 at the top of the lower tank, which is the same as before, to section S at the suction inlet to the pump. Thus, we need to determine all the head changes up to the suction inlet that determine the pressure at the suction inlet. For this case, the velocity at section 1 can still be assumed to be 0, but the pressures do not cancel, and the velocity at section S will definitely not be 0. However, we will assume it is still turbulent with a flat profile, and the kinetic energy coefficient can be approximated as 1. Using these values, we get the following relation for the conditions at the suction inlet. Next, we recall the definition for the net positive suction head available. Substituting in our result above for the first two terms on the right, we get the relationship shown. This result gives us an equation that first compares the starting pressure for our system, in this case atmospheric, to the vapor pressure of the liquid, and then accounts for changes in elevation and head losses to determine the conditions at the suction inlet. Evaluating these three terms, we get 33.1 feet for the first one, 5 feet for the elevation change up to the suction inlet, and 24.5 feet for the major and minor head losses. Note that for this calculation, we use only the entrance loss, length of pipe before the pump, and 1 elbow for just the suction side. Combining these values, we get that the net positive suction head available is 3.6 feet. Note that if this had been below 0, the pump would definitely cavitate. Because it is above 0, we need to compare it to the net positive suction head required, which was 7 feet, to check for cavitation. Because it is below this value, the pump will likely cavitate. Thus, to use this pump, we would have to reduce the losses before the suction inlet. Several options include lowering the pump and reducing the major and minor head losses before the suction inlet. Finally, note that the first term indicates that 33 feet is the maximum height that water at standard temperature and pressure, starting at atmospheric pressure, can be sucked upwards before it completely vaporizes at the suction inlet.